Imagine we have the graph of an arbitrary function, this one shown in blue. Let's say we're interested in finding the slope of the tangent line at a specific point, the orange line you see here. Normally, calculating the slope of a line is easy, as long as we know 2 points on that line. But unfortunately, in this case, we only have one. So, what can we do? Let's try a different approach. We can draw a second line, shown here in red, and fortunately for us, we can calculate its slope, since we have the coordinates of 2 points. The first point has coordinates, x comma f of x, and the second one is x plus delta x comma f of x plus delta x. To find the slope of this second line, we can recall from analytic geometry that if we know 2 points on a line, we can use the formula m equals y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1. In our case, that becomes m equals f of x plus delta x minus f of x divided by x plus delta x minus x. We can simplify the denominator and we're left with m equals f of x plus delta x minus f of x divided by delta x. Remember, delta x represents the horizontal distance between the 2 points. Now suppose we want the secant to be shorter, but still start at the same original point. We just choose a second point that's closer. As you can see, the slope would still be calculated the same way, only now with a smaller delta x. We could keep repeating this process, making delta x smaller and smaller. Watch how, as we reduce the length of the secant, its slope starts to resemble more and more the slope of the tangent line. Until eventually, if we could theoretically draw a line where both points are the same, the slope of that hypothetical line would match exactly the slope of the tangent line. Now, here's the catch. That slope can't be calculated using the formula we've been using, because as you can see, delta x would have to be 0, and division by 0 is undefined. But guess what? The limit is defined, and we can evaluate it. That's why the slope of the tangent line is defined as the limit as delta x approaches 0 of f of x plus delta x minus f of x divided by delta x. This is the definition of the derivative, and that's why we say the derivative is the slope of the tangent line. The derivative of a function measures how the value of the function changes. It's a fundamental tool in fields like physics, engineering, and economics. It tells us the rate of change of a function, or, from another perspective, the slope of the tangent line at any given point on the function's graph. In essence, the derivative gives us a powerful way to understand how things change, instantly, precisely, and elegantly. Whether we're modeling the speed of a car, the growth of a population, or the shape of a curve, the derivative captures that hidden motion at every point. It's not just a formula, it's a bridge between algebra and geometry, between numbers and motion. And through it, we don't just trace functions, we reveal their behavior.